Okay, now we can start talking about voltage. From my last video, I talked about electric potential energy, so we're ready to dive into voltage. One thing I didn't talk about in my last video is, hey, what if you have a positive and a negative charge? How does U work there? Because if you remember from our equation that we kind of figured out, we said that U is equal to K, which is our constant, 1 over 4 pi epsilon naught, whatever, K Q1, Q2 over R, where R is that distance between them. So use that's the equation for U. If you have a positive charge here and a negative charge here, you get a negative U. You get negative potential energy. Well, and remember, energy is a scalar, it doesn't have direction. So negative 1,000 joules versus negative 10 joules. Negative 10 joules has more like energy. There's more potential energy, right? Because it's a number line, right? Negative 1,000 is a really small number because it's a negative. It's a scalar. So there's no such thing as like magnitude of U. You can do the absolute value, but there's no like magnitude because it is magnitude like that. It's a scalar. So negative, positive. How can you have negative U? Well, the only real difference is, hey, the force is now going to be attractive, which means you start. So let's do a little pie chart here, or a little diagram. You start with a certain amount of negative K. You start with a certain amount of negative energy, a negative amount of U, and you start with no K, right? Now there's no energy being added or created, or there's no, it's never added or created, but there's no work being done is what I meant to say. And now it's gonna be moving towards U, or why am I saying moving towards U? Moving towards the proton. It's gonna have some K. In order for energy to be conserved, we need to have a total amount of initial negative energy. In order for energy to be conserved, hey, guess what? Our U gets even more negative to kind of balance out, cancel out some of that positive kinetic energy. So how does this work with our equation? Well, yes, because as they move closer together, R gets smaller, which means this whole fraction kind of gets bigger, right? Because it's an inverse relationship, but it's all negative. You get a bigger negative number. Hey, that works with our model. Energy is conserved. Cool equation. So now we can start talking about electric, or not electric. I'll just say voltage because it sounds cooler. Now, what if we have this proton right here, and we want to place from a distance r, we want to place a little point charge q. Okay. Awesome, I did that. I placed a point charge q. Now, it could be positive and negative. Let's just say it's positive. If it were a positive charge and I doubled it, I did 2q, what's going to happen to the potential energy between them? It's going to get 2 times bigger. So, yeah, there you go. Makes sense because U, I don't know why I erased the equation already here, is equal to K Q1 Q2 over R. So if this is Q1 and this is Q2, hey, 2 times Q2 means 2 times potential energy, right? That makes sense. Now, what if I make this 4 times bigger? Hey, guess what? 4 times a Q, 4 times the potential energy. There's some sort of constant ratio, okay? If I were to take U and divide it by Q, Q2 specifically, and I'll do uppercase because I like uppercase. It's some sort of constant ratio, not capacitance, but constant. So 2 times Q2, hey, that doubles the potential energy. Great, it's a constant, right? Well, what is this constant, right? What is the constant? Like, what is this equal to? What is this constant equal to? Well, if we just plug in this equation right here, you get K Q1 Q2 over R over, because this is still U, over Q2. The Q2 cancels out. So, and that makes sense, right? Because 2 times Q2, 2 times Q2 here, hey, it balances out. So we're just left with K Q1 over R. This is what we call electric potential. It is the amount of energy, potential energy, per unit charge, okay? So if you have double if you have double the charge here, you're gonna have double the potential energy because this is the constant. We call this electric potential, right? This Q1 is constant, this K is constant, this R is constant. That ratio between U and Q2 is a constant. That's all what electric potential is. It's just like this ratio, right? It's just U over Q, right? We call this we use the letter V for this. And what we can really say is that, okay, U is actually just equal to Q times V. So for a certain electric potential, there's going to be, multiplied by the charge at that potential, you get U. So what do I mean by that? Well, it's like okay, so let me explain it like this. Q1 creates this electric potential at this distance. So if I were to kind of get rid of Q2, there's no charge there, okay? This is the only charge in the whole universe. We could say that if we wanted to. But there's still going to be an electric potential right here. This charge, just like how it causes an electric field, it's causing this electric potential right here. Why is, there's an electric potential right here, right? Which means if we multiply whatever that electric potential is, how do I know what the electric potential is? I use this equation, KQ1 over R. Okay, Q1 times R times 1 over 4 pi epsilon naught, right? Our constant. You get your the electric potential right here. Now, if I were to put a charge Q1 right there, if I multiply it by the electric potential, which I just found, I get the potential energy between them. Okay, cool. Why do I care? Let's say, let's say we move, let's say this charge is here. It's right now R, A, and it's going to move to R, B. Think to yourself, okay, at point A and point B, is there an electric potential, okay, is the electric potential different here than to here? Think to yourself for a second. Did you think? I hope you thought about it, because yes, the electric potential energy the electric potential is different. If I were to take the same charge here versus here, I would get more potential energy here, hence there's more potential here, okay? Remember, it's just the ratio, right? If this is like the simplified ratio and you cancel it out, bigger R, less potential. So I want to figure out, okay, there's going to be some sort of potential difference, okay? There's going to be some sort of difference in potential from the potential here minus the potential here. That's what I'm going to call my potential difference, okay? So if I take this minus that potential, that's our potential difference, right? Because there's more potential here. So this is going to be some sort of positive number. Now, how do I figure that out? Well, what I know is that U over, so here, let's do this. U over Q is going to equal the potential at that certain point, right? So if I do change in U, the change in potential energy over Q. I know the potential energy changed because we can also use this equation. There's less potential energy here because there's less potential. So the change in U is the same thing as U final minus U initial over Q. So then I can kind of split up the fraction and be like, okay, U final over Q minus U initial over Q. And then, oh, U final over Q, well, that's just K Q1 over R, right? Q1 over R. This is just voltage. This is the final voltage minus the initial, sorry, not voltage, electric potential. I don't know if they're the same thing yet, so you're just going to have to, I'm just going to call it electric potential. The electric potential here is RB, right, minus the electric potential here, which is RA, because that's the initial sort of spot initial UG. Sorry, just U, initial energy. Okay, so this is just the voltage at B minus the voltage at A. Well, that's pretty close to what we want, but I'm going to say, okay, well, this is still change in UG over Q. I want to make this positive, I want to make this negative. That's the same as just multiplying by one negative. So I just multiply this VB minus V, I multiply by negative 1. I got to do the same thing here. You get negative change in U over Q. Negative change in U, that's just the work done by the electric force, by our conservative force. And you can check out my last video if that doesn't really make sense, what I just said. Right? Because, you know, if it's work done by conservative force, it's just negative change in U. So the work done by the electric force is going to equal VA minus VB. So, what this tells me is that the work done by the electric force, in other words, the work done on this charge by this charge is going to equal the charge itself, right? The charge that got work done on it, VA minus VB, the potential difference. We can also call this change in V. But I don't really like change in V because then you think of V final minus V initial. This is kind of V final, but we're doing V initial minus V final. So instead, I like to do negative Q change in V. All right. So what this means is okay. So let's think about this. If this work is positive, right? In all cases, it's kind of gonna be positive, right? Then what we know is that our change in electric potential is going to be negative. It has to be negative mathematically because this is a positive. Hey, we gotta have a negative to multiply with this negative to get positive. So the change in potential is negative, right? Which means the final is low and the initial is high, right? Because if you do low minus high, you get negative. My electric potential here, this is a final. Maybe this is 30 volts. I don't know. Maybe this, and oh, I gotta talk about one whole time. A horrible teacher. I didn't even talk about units. 60 volts. Then hey, low minus high is a negative. So that means my charge, if this is negative, it went to low, right? Because final is low, initial is high. My charge went from high to low. So there you go, right? We'll start talking more about high to low voltage and what that really means and how do we work with negatives. And I'll probably make a part 2 on this video. What I want to leave you off with, I didn't even talk about this. This unit is joules per coulomb. How do I know it's joules from joules per coulomb? Because I have energy over Q. The equation for voltage is equal to U over Q, and then the work done by the electric force is equal to negative Q change in V. Okay, so voltage does have joules per coulomb, and we call that volts. This is 1 volt. Thank you for watching. I want to see how long this dastardly video was. Oh, 13 minutes, that's not bad.